Okay, hello everybody. I hope you had a nice weekend. So for Monday and Tuesday's assignment, you're going to have to first watch this video and then do some assigned work. So today we're going to be talking about sound intensity and resonance. The objectives of today's class are to learn how to calculate the intensity of sound waves, to be able to relate intensity, decibel level, and the perceived loudness, and to explain why resonance occurs. So just a little bit from our PowerPoints. As sound waves travel, energy is transferred from one molecule to the next because you know that there's disruption of matter and the particles collide. The rate at which energy is transferred through the unit of area of the plane wave is called the intensity of a wave. So the rate is pretty much how fast that energy is moving. So power is defined as the rate of energy transfer. Intensity can also be described in terms of power. So this is the formula we're going to be using. So the first definition said intensity is equal to the change in energy divided by time over an area. So how fast the energy is moving over an area. Another form we're going to be working of the formula is saying, okay, change in energy over time is the same thing as power. And the area, it's the surface area of a sphere, which is 4 pi r squared. So this formula over here, it's pretty much that same formula applied to the area of a sphere and using power instead of energy over time, which we know are pretty much the same thing. So that's the formula we're going to be using. So if you go to your textbook, let's go over an example before you do your assignment. Part of your assignment is this page down here. So what is the intensity of the sound waves produced by a trumpet at a distance of 3.2 meters when the power output of the trumpet is 0.20 watts? So they're giving me the power and they're giving me the distance between the source and the person or whatever is hearing, which is your radius. Because remember that sound waves spread out in all directions, creating a sphere. So all you have to do pretty much here is plug things in. Go ahead and do that to make sure you can use your calculator. Just keep in mind what's important here is that if you're going to plug it in your calculator, all at the same time, you have to use a big parentheses around the denominator. If not, your calculator is going to take those factors at the bottom and take them to the numerator, and your answer is going to be wrong. So make sure you can do that problem right now, and then you can do this part of your assignment, or you can watch the entire video and then come back and do it, whatever you prefer. If you do this first, then you have to continue your video later on. So let's talk about the intensity of a sound. The unit of intensity, if you look at the formula, is watts over meter squared, which is power over area. The intensity equation shows that the intensity decreases as the radius increases. So as you get farther away from the source of energy, the intensity of sound decreases. That makes sense. If you're very close to your TV at a high volume, it's going to seem like the sound has a lot of intensity, as whether you move away, the intensity is going to decrease. This occurs because the same amount of energy is spread out or dissipated over a larger area because the sphere gets bigger as you go farther away from the source of energy. So remember when we talked about sound in the prior section, we talked about frequency of sound. And now we're talking about intensity. So both factors involve in how we listen to sound. So if you remember when you did your lab, when we were doing the very high frequencies, I asked you guys to decrease the volume, okay? Because if you left the frequency very high and the intensity very high, you could actually hurt your ears. Because that's why they call it up here the threshold of pain, because that's going to make your ears hurt when the frequency is high and the intensity is also high. Obviously, your computer is not able to get to that threshold of pain. So when I ask you to decrease the volume, we're pretty much staying down here. So if you notice that that's the 20 to the 20,000 where we played with our frequencies. Now we're also putting in intensity. Whenever we're talking, our speech region is going to be in this area. Some people have higher voices and some people have lower voices. Some people speak at a higher volume or a lower volume. This is the music region, because usually you play music much louder than you then you speak, and you also have different frequencies with music because you have instruments. And then over here, it's what is the area of sound. So sound can pretty much be between these frequencies and those intensities. So the intensity of a wave approximately determines its perceived loudness. So intensity is a numerical value, and loudness is like an adjective, like high. Is it loud or is it not loud, like our volume? That kind of thing is not a numerical value. However, loudness is not directly proportional to intensity. The reason is that so they're not directly they are proportional, but not directly proportional. That means that if one of them increases, the other one's going to increase, but you can't make proportions out of them because the ratio changes. The reason is that the sensation of loudness is approximately logarithmic in the human ear. So relative intensity is the ratio of the intensity of a given sound wave to the intensity at the threshold of hearing. So it's not a linear, when you graph it, it's not a linear function. It's pretty much a logarithmic function. So because of the logarithmic dependence of perceived loudness on intensity, using a number equal to 10 times the logarithm of the relative intensity provides a good indicator for human perception of loudness. So when you have the intensity, you multiply 10 times the log of the relative intensity, and that gives you a perception of loudness to be able to compare it to another loudness. You're not going to be doing any numerical problems here, but you do need to understand what this is talking about, and it's going to help us out in a table. This is referred to as the decibel level. It's a dimensionless unit called the decibel. It's used for values on this scale, so I'm going to link a video that explains about decibels in a second. I'm going to link it up on the post, but not inside of this video. So here's an example of different decibel levels, and I do want you to notice how they're all exponential in intensity, but the decibel level is only increasing, not exponentially. So look at this, from 0 to 10, and then the intensity goes by a factor of 10. But when you go from 0 to 20, it goes by another factor of 10, which is not 2, if that makes any sense. I'm going to show you that with a video. I don't want to take up too much time in this video. So let's just look at some of the decibel levels of some common sounds. Rustling leaves, 10. Mosquito buzzing near your ear would be a 40. Your vacuum cleaner at home, which is pretty loud, that would be a 70 decibel. Auto horn at 1 meter, 110 decibels. The threshold of pain, so anything about 120 decibels is going to hurt your ears. Thunderclap or machine gun, that we know that these could actually hurt your ears, are 130, and a jet airplane would be nearby, 150. That's why people that work near airplanes in the airport, they have to wear protective hearing devices. And then we're going to be talking about resonance. Resonance, it would be, I'm also going to post a video on resonance next to this video up, and you have to watch it and take notes. If one of the pendulum here, so here we have 4 pendulums. If you notice, the 2 blue pendulums have the same length. If one of the pendulums is set in motion, its vibrations are transferred by the red rubber band to the other pendulums, which also are going to begin vibrating. So this is going to take the motion over to all of them. This is called a force vibration because we're only producing a motion or a vibration in another object due to the vibration in the object it is connected to. Each pendulum, it starts vibrating at different frequencies because of their length. So that frequency at which it starts vibrating is called its natural frequency. Resonance is a phenomenon that occurs when the frequency of a force applied to a system matches the natural frequency of vibration of the system, and this results in a large amplitude of vibration. If the blue pendulum is set in motion, which one is going to have the same natural frequency as the blue pendulum? The other blue pendulum. So only the other blue pendulum is going to eventually resonate. So I'm going to link that video I want you to watch so you understand resonance more in detail. And after that, I do want you to copy this diagram in your notes, which is the human ear. The human ear, you already studied about this in the past, but it's a good thing to know what's going on. It's divided into 3 sections, the outer ear, the middle, and the inner ear. Sound waves travel through the 3 regions of the ear and are then transmitted to the brain as impulses through nerve endings on the basilar membrane. So remember, it's all about vibrations. So when sound reaches our ear, it's the air particles inside of our ear that are vibrating. So sound is only vibration. It is our inner ear that takes that vibration and interprets it as sound in our brains. And I'm also going to be linking another video on human hearing next to this one. So now make sure you watch this video, watch all of the other small videos I'm going to send you, take notes on everything, and then do your homework assignment. Have a nice day.